via hyperbolically embedded subgroups.
Okay, thank you very much. It's a pleasure to be here. Good morning, everybody, including those watching the live stream. And happy birthday, Federico. So, okay, let's get started. So I want to talk about my perspective on how one should try to understand the bounded cohomology of an acylindrically hyperbolic group, which is elaborated upon across a few papers. And I'm going to assume that most of you have seen acylindrically hyperbolic groups before and are vaguely familiar with it. If not, what I'm going to say is non-trivial for hyperbolic groups too. So you can just think about hyperbolic groups. So basically the only thing I'm going to say about acylindrically hyperbolic groups in general is the theorem that you can take as a definition of acylindrically hyperbolic groups. So all groups I'm going to talk about are finitely generated. Often is not needed, but let's stick to that. So a group G is acylindrically hyperbolic if and only if G contains an infinite hyperbolically embedded, which I'm going to define in a second, subgroup of infinite index. Okay, so hyperbolically embedded and then two non-triviality conditions. Okay, so what are those? Let's go here. So this is not the original definition, so it's again definition slash theorem. And we have our group G, and let's say that G is generated by some subset Y. And I'm not assuming that Y is finite. Y is possibly infinite. Okay, so but you can just think of G as a hyperbolic group and Y as a finite generating set. So right, and I'm going to impose this condition that you don't really need in general, but makes things more concrete. And I'm gonna just look at this setup for this talk. So I'm gonna assume that the Katy graph of G with respect to Y is hyperbolic. Okay, then a subgroup is hyperbolically embedded. Which is denoted hyperbolically embedded in G with respect to Y. So denoted H hyperbolically embedded in GY. If the following holds. So the first condition is that so we took a possibly infinite generating set, so we are possibly forgetting a lot of the geometry of G, but we are not forgetting H. So H is Qi embedded in the Katy graph. So H is Qi embedded in KGY.
So H is finitely generated?
Yeah, H is finitely generated. Okay, so in particular it's hyperbolic, since we added that assumption on the Katy graph. And the second condition is a geometric version of almost malnormality. So as Jinying said, almost malnormality or almost malnormality corresponds to coarse intersections of cosets being, well, you talk about lifts, so it is the same with cosets. Coarse intersections be bounded, so let's write it. So for every G not in H, so we look at the diameter in this Katy graph of a neighborhood of GH intersected with H. So both the neighborhood and the diameter are taken in the Katy graph, in that Katy graph, not in the not in G itself. So this diameter is bounded by a constant that depends on C. Okay, so maybe a tiny picture. So two cosets kind of have bounded interaction, but then they go off in different parts of your group. Okay, that's the definition. I should write a few names. So the notion first appears in DGO, Damanigi-Ardaozin. This exact statement is in a paper of Michael Hall and a paper of Antolin Minazian and myself. Okay, so maybe right. So if y was finite, then we were just really saying that we were taking a quasi-convex, almost non-normal subgroup of a hyperbolic group. So let me remark on why taking Katy graphs with respect to infinite generating sets is not a crazy thing to do. So there's some version of Milnor-Schwarz that works for just co-bounded action, not proper co-bounded, just co-bounded. So, and Katy graphs correspond to the squiggly arrow, correspond to co-bounded actions. So G. So in fact, say the mapping class group is a cylindrical hyperbolic, and you're gonna consider the action on the curve complex, and there's some generating sets that the Katy graph of the mapping class group is Qi to the curve complex, and that's the generating set we're talking about there. I mean, that's one possible generating set that we're talking about there. Okay. Very good. So the setup for the talk is let me fix the notation for all the theorem. So general assumptions are that we have a group G and we have generated by some possibly infinite Y, and we assume that there exists a hyperbolically embedded subgroup with respect to this generating set. So H is infinite and of infinite index. Oh, right, you can check that the group itself is hyperbolically embedded. No, the group itself is hyperbolic. Forget about that. Finite subgroups are always hyperbolically embedded. And in the more general setup, the group itself is hyperbolically embedded with respect to some generating set. Okay, and also I'm gonna, just because it simplifies statements, I'm gonna assume that G has no non-trivial finite normal subgroups. So it turns out that an acylindrical hyperbolic group has a unique maximal finite normal subgroup. And so the statements that I'm going to give might be, in the if you drop this assumption, have to be modified to keep that into account. So all the statements I'm going to say are true up to finite perturbation in the general setup. Mm-hmm. Yeah.
Otherwise, it's not. I mean, if you have y infinite and the space is hyperbolic, doesn't mean that there is a finite generator set.
Yeah.
So you suppose that there is some another one.
Yeah, you don't. For most of what I'm going to say, you don't really need it, but I prefer to stick to that case to avoid saying false things, which would probably happen otherwise. All right. So, in fact, turns out that if you have one hyperbolically embedded subgroup, you have plenty, and that's very good for applications, to choose your hyperbolically embedded subgroup in the way you like. And in fact, they're even generic. So I'm going to write this because it's going to be needed later. So the theorem with Joseph Meyer is that if you, under those assumptions, so we can take two independent simple random walks. So generic in the sense of random walks, not in some sense. Independent. Let's take the simple random walks. Simple random walks. Okay. That's it. Okay, so then the following things hold for the following. Hold with probability going to 1 as mn going to infinity. Okay, so first of all, so we're going to look at the subgroup generated by these two random elements. Okay, and the subgroup generated by these two random elements is a free group on two generators. In fact, freely generated by those. And also it is hyperbolically embedded. Okay, so there's many of those. Right. So let me go here. Right, I should say that theorem has many precursors, and if I mention one, I would have to mention all of them, so I'm not going to mention any. But I should. Okay. Right. Okay, so of course I'm not gonna be able to prove any theorem in detail because I'm gonna want to talk about a few. But I want to draw one picture for every theorem. So let me draw the picture for this theorem. So what happens is you can look at the KD graph of GY. So it turns out that, okay, let's take these two random walks. So the random walks make linear progress in this metric. So they're linearly far from the base point, and they form a small Gromov product generically. And so this easily tells you that you get a free group. Usual kind of hyperbolicity arguments. Okay, that's for part 1, and the more serious part 2 uses, so one of the key ideas that it uses is that there's no matching, which means that there does not exist some group elements when you look at the action on this space that do the following. So you have the base point, xn, the geodesic, connecting them. Then there's no group element that moves this a bit far away, I mean enough far away in a way that there's an overlap. Okay, because you can convince yourself that two random words don't have long common subwords. Their long is, say, 1/10 of their length. That's more or less what goes on. Okay, that was the cylindrical hyperbolic part. Now let's go into bounded cohomology, and I will just stick to quasimorphisms to make things concrete. So let me recall the definition of quasimorphisms. So if you have a map from a group to R, we say that is a quasimorphism. If it's whenever you look at G and H, phi on GH is approximately phi of G plus phi of H. So we take the supremum. Okay, so if this supremum is 0, then phi is a homomorphism. All right, and it's convenient to often to look at quasimorphisms, homogeneous quasimorphisms. So phi quasimorphism is homogeneous if phi of G to the so if it is a homomorphism at least restricted to cyclic subgroups. Okay, and second bounded cohomology, in fact, the exact part of the second bounded cohomology, but pretend that E is not there, can be identified with quasimorphisms. So the space of quasimorphisms, so the quasimorphisms phi from G to R, mod out by the trivial ones. So how can you trivially be a quasimorphism? Well, if you're a homomorphism, for example, or if you're a bounded function, also true, or if you're a sum of those. Okay. And the cool thing about about homogeneous quasimorphisms is that they allow you to get rid of that part. So this is the same as homogeneous quasimorphisms mod out just by homomorphisms. So it's kind of a canonical representative within the bounded perturbation cos. All right, and example. So the canonical example is due to Brooks. I expect many of you to have seen it already. So if you take, let's just take the free group on two generators. And we can assign the value to an element of the free group that I think of as a reduced word, as the number of occurrences of, well, we can fix any word we want. Let's take the commutator. So the number of times that the commutator appears in W minus the number of times minus number of times it appears in W inverse. Okay, so restricted to the subgroup generated by the commutator, it is a homomorphism, and it's an extent. So you cannot extend that homomorphism to a homomorphism on the whole of F2, but you can extend it to a quasimorphism on the whole of F2. So facts are that phi is a quasimorphism. That's, you can easily check that. And so the fact that it's unbounded on the commutator subgroup is going to easily tell you that the same is true for the homogeneous representative, and hence these two things tell you that you can take, so in the bounded cohomology of the free group, there's a class which is represented by phi, and that class is non-trivial. Okay. That was the introductory part. Let's now start discussing the bounded cohomology of acylindric hyperbolic groups. So, and first of all, one would like to know how big it is. And it's very big. So with you can use different words rather than a commutator subgroup, and then in fact show not only that the bounded cohomology of the free group is non-trivial, but that it's infinite dimensional, and this somehow passes up to the bounded cohomology of acylindric hyperbolic groups because of the following. So this was proven by Hall and Ozin. I'm also gonna give the statement for higher degree bounded cohomology, which is in FPS. So if you have a subgroup, so I guess let's just assume star. So if you have a subgroup which is hyperbolically embedded, so whenever you have a subgroup, you have a restriction map. So the restriction map from the bounded cohomology of the ambient group to the bounded cohomology of the subgroup. Okay, so for quasimorphisms, it's just saying that I restrict the quasimorphism. And this map is surjective. Okay, so you can take, oh, okay, I'm going to write the corollary in a second. So let me write it more concretely. So I forgot to give a notation for the set of homogeneous quasimorphisms. So let's do that. Let's remedy this right away. HQ1. So any homogeneous quasimorphism can be extended to G. Yep. So on the nodes without adding homomorphism. Yep.
What about if you remove the E? Is it still true? If you remove exact?
No, it's not true if you remove the E's in general. It's Yep. So let's see if I can remember it. So you take, let's say, a hyperbolic manifold with totally geodesic boundary. So maybe connected totally geodesic boundary, and dimension n. Let's see. So you have. Okay. So you have the restriction map and -1, I guess, at the level. At the level of bounded cohomology and at the level of just usual cohomology. And there's the comparison maps. Oops, I should have. Yeah, and there's the comparison maps. But what am I doing? Well, yeah. And so the
Volume of the.
yes, so the fundamental class here has a bounded representative. So if this map was surjective, you could have a pre-image here, but that's not in the image of this map. Okay. Right, so corollary of the theorem. Is there anything else I wanted to say? No, I guess it's okay. So corollary of the theorem is that the second bounded cohomology of an acylindrically hyperbolic group is infinite dimensional. Because you have a free hyperbolically embedded subgroup. I mean that's an overkill, but you can deduce it from here. And yep, so that passes up. And the same is true in dimension 3 because due to work of Soma, the third bounded cohomology of a free group is also infinite dimensional. Okay, let me briefly mention that if you analyze that construction a bit more carefully and you choose carefully what to extend, then you get that the dimension of the zero norm subspace of H3b, so the alpha H3b, so those with Gromov norm equals 0, that's also infinite. Okay. I guess for whoever cares, which might be 3 people in the world. Okay, so right, I promised a picture for every theorem, so let's draw the picture for this here. And so there's a long story behind that theorem too, and many people should be mentioned. So it all starts with the Brooks construction, and then at some point somebody realized that there's more geometry than you would think at first when seeing that definition. And basically the geometry is what I'm going to draw now. So you have, once again, you have your Cayley graph, GY, and you have, okay, so maybe the identity is here. And you have all these cosets floating around. No, let me draw it like this. Let me draw one here. All these cosets of H, so maybe, yeah, these are all cosets of H. So, and now you have a quasimorphism on H, and you want to extend it. What do? So you want to assign the value to some g. So you look at a geodesic from the identity to g, and what's it gonna do? It's gonna have some sub-geodesics that follow travel cosets. Okay, they're disjoint because of almost malnormality, and they actually follow travel because of quasi-convexity. And what can you do? You can. So when you look at the entrance and exit points, so the difference is some element of h. So you know how to assign a value to each of these segments, and you just take the sum. Okay, you sum these. Sum phi of these. Okay, so this doesn't quite work essentially because the entrance and exit points are only coarsely well defined. So, and there's 84 ways to solve these technical problems, which is the reason why there's 84 papers that more or less do this thing. Okay. Right, now there comes the crucial point of the talk. So if you take something away from this talk, it's the following. So now so when you look at that, what you might think is that the following is worth studying. So I don't know, let's call it problem. So maybe you don't look at just one of them because one is not going to be enough to, one hyperbolically embedded subgroup is not going to be enough to control the whole bounded cohomology. But you could look at all of them, so or some collection of them. So you can study not just a restriction map, but a product of restriction map. So study that. So product, let's say over some collection of hyperbolically embedded subgroups. Okay, that's okay. Okay, so I claim that it's studying, and I claim that we can get that there's a lot of information in this map, say for the product of all hyperbolically embedded subgroups. So that's really what controls the bounded cohomology of G. So it's hyperbolically embedded subgroups and their bounded cohomology. So as right, and the first thing I want to tell you about this about that map is that it's injective. Okay, so it really, so which made my claim sensible. Okay, so assume star. So let's take a look at all three hyperbolically embedded subgroups. 3 on 2 generators. Okay. Then this restriction map is injective. Okay, let me write it more concretely. So, i.e., if you have so in degree 2, let's just write degree 2. So I don't have to rewrite that here. So i.e. For any phi which is a homogeneous quasimorphism on G, there exists a free and hyperbolically embedded subgroup. So phi not a homomorphism. Phi not a homomorphism. And there exists H, so that when you restrict it to H is also not a homomorphism. All right. So all constructions of classes in the bounded cohomology of acylindrically hyperbolic groups or groups with hyperbolic type properties that I'm aware of come from some sort of extension procedure, and this tells you that, well, there's a good reason for that. There's basically the only thing there is. All right. So this one is true without the E, and but it's false in degree 3, even for a surface subgroup. So surface group. Okay. Right, and let's go here. Okay, so in fact this is a probabilistic argument. So what we actually prove, and I mean this is for it's going to be true for any group, is that any group G and phi G2R, that if you have xn ym, if you have independent, so due to laziness, I have to add the word lazy here, due to our laziness, improving that theorem. Lazy simple random walk. So lazy just means that you can stay where you are with definite probability every time. Blah blah blah. The probability phi is a homogeneous quasimorphism. The probability that phi xn ym minus phi xn minus phi ym is non-zero. Oh, okay, fine. We'll just do non-zero. This is larger than epsilon. So epsilon is independent of n of m, and so guess that epsilon depends on your phi. Oh, and for every n and m large enough, I guess. Okay. So you combine this with the genericity of hyperbolically embedded subgroups, and you get what you want. All right. What else did I want to say? Oh yeah, there was another comment before I draw the picture. So another comment I want to say is that I believe that this is non-trivial even if you just look at the restriction map to the bounded cohomologies of free groups without the hyperbolically embedded subgroups. I don't know how to prove that non-trivial quasimorphism is non-trivial when restricted to a free group, say for a hyperbolic group. how to prove it besides going through this. Okay, so what's the picture for this one? The picture for this one is that whenever you have, okay, so let's call this guy, so the coboundary, so let's call it delta x and y. Okay, so what's this degree 2 thing? So a cohomology class in degree 2 is something that assigns a number to triangles. So, and how is a quasimorphism a cohomology class? You can assign to a triangle like that the number delta GH. Okay, and so right. So since you're starting from something that's not a homomorphism, you know that there exists there exists one pair G and H, so that the delta GH is non-zero, just one. So, and you want many. So you have to come up with some way of constructing many other pairs. So, and the way you do that is you look at tetrahedra like that. So where x is an arbitrary, so you can put x an arbitrary thing. And the point is that the sum over the faces of this tetrahedron is going to be, of the deltas, is 0. So if one of them is non-zero, then there's another face which is also non-zero. So delta GH non-zero. There exists a face, another face with delta non-zero. And yeah, so the proof is actually relies a lot on things like this, on observations like this, where you construct a lot bigger. Okay, thank you. Okay. Very well. And now we can move on, I think. Yes. So that's about injectivity. So let's go here. So that map is never going to be surjective, but the hope would be to understand the image. So if you understand the bounded cohomology of free groups, I don't know, they are the ones. It's the one that's closest to being understood in some sense. You know that that map is injective. You understand the image, then you're in good shape. So I don't have a guess for what the image should be. But it seems like a good start to look at finitely many coordinates at a time, and then maybe there's gonna be some sort of description in terms of what happens on finitely many on every finite subset. That's so let's look at finitely many coordinates. So basically we've looked at one coordinate there. So okay, and So let's consider A finite, and let's maybe make a definition. So let's take finitely many. Well, for now, just subgroups. And let's take homogeneous quasimorphisms on them. Okay, so if there's any hope to extend them, they'd better be compatible on the intersection, on the various intersections that you see. So, but in fact, so if you think about it for a second, homogeneous quasimorphisms, you realize that homogeneous quasimorphisms are invariant under conjugation. So it's actually more about intersections of conjugates. So we say that that family is intersection compatible. So if whenever you have something in HI which is conjugate, so for every HI, for every Y, so if X is conjugate in G to Y, then the values better be the same. That's the minimal possible requirement that you can impose on a family of quasimorphisms to for them to extend. And the theorem that's going to appear here in a second says that that's the only requirement. So it's, in some sense, when you restrict to finitely many coordinates, that's as surjective as it can be. Okay, so this is the final one. So let's take, so under our usual assumptions, so let's take finitely many hyperbolically embedded subgroups. Okay. So then for every intersection compatible family, there exists an extension. All right. And so, okay, let me add it as an official statement. So but this also tells you that that whenever you have a family like that, it's the restriction map is not going to be injected. So when you look at the restriction map to those coordinates, it's not going to be injected. So for every A as above, let's add infinite index because okay. Oops, not injected. Because if you, I mean, this is just a corollary, basically, kind of a corollary of this. Once you know that you can add a collection of hyperbolically embedded subgroups with the property, so the new one needs to have the property that it intersects the conjugates of the other ones in a infinite subgroups. And this is almost in DGO, nearly in FPS, and almost in Abbott-Damani, but a little bit more. Okay. And yes. So that's the current knowledge about this, which I'm gonna elevate. And let me just say, let's see, 3 minutes. I'm not gonna, okay, I want to finish at 5:2, so I'm not gonna write the statement, but so what I want to say is that, so like 5% of this paper is about bounded cohomology, 95% is about intersections of conjugates. So that's what you need to understand. So let me just write that you need to understand intersection of conjugates, intersections of conjugates of hyperbolically embedded subgroups but in fact, so yeah, this used to be two papers. They got combined in a special way to the paper by Sam and Mahan was about stable subgroups. Well, is about stable subgroups. Of which hyperbolically embedded subgroups, hyperbolically embedded subgroups are a special case. In particular, let me just write the word, so finite height and width. So generalizing stuff known for quasi-convex subgroups of hyperbolic groups. Okay, so the last picture, why was that true? So remember how the extension worked? So you have all these cosets. And so if you want to extend from some subgroup, you look at the geodesic from 1 to G. It fellow travels some cosets, and you were going to look at these subintervals here. So in this case, you have maybe two cosets of two subgroups. Do something like this. So you don't know whether to assign, say, this subinterval here to the white or to the purple. But the point is of intersection compatibility is that it doesn't matter. So this is why I guess you should believe that this is true. And I think that's all I want to say. Thank you.
Thank you very much. Are there any questions?
In the last theorem, can you try to do that by successive Dehn fillings?
Successive Dehn fillings. Yeah.
I think.
Right. That's.
So in the end, you get something that.
Yeah. So.
In which
if you can
essentially all the HI should be in the kernel. So
I mean, this can have
yeah.
They can intersect.
Not well, yeah, successive. So one of the. I don't know.
Maybe. I mean, I'm not saying that it's that the fact that you can add one is a super deep fact, but yes, that there's many. So the way we do it is so you can use genericity by you add h1 to a generating set, and then you're gonna have generically something that's hyperbolically embedded in G comma H union H1, and same true for all k. So since there's finitely many with like probability going to 1, it's gonna be hyperbolically embedded. I mean, yeah, all pairs are gonna be hyperbolically embedded. That's I mean, but yes, or you can do a construction by hand, for sure. I'm sure you can. Yeah.
Thank you. More questions? So then let's thank the speaker again.